I assigned homework 1, assignment 1 this weekend, yeah, but many students noticed I didn't give you exercise practice question set for module 2. Yeah. So now I feel I do not plan to give, because the module 2 material, so our homework assignment and the quiz 2, it's enough for practice, yeah, because we do not have much content in module 2. So if we only practice in homework assignment 1 and quiz 2, that should be enough. Yeah. So module 3, I may give you practice question set again. Yeah. So that's one thing. Another thing is some students also ask me about the flashcards. Yeah, I didn't create for module 2. Yeah. Also, yeah. Yeah. So if I can find time, so I will do. So I'll try my best. Yeah. So because some students told me, it's good for study. So yeah, I understand that. Yeah. So if I can find a little time, so I will, do some more flashcards. Yeah. All right. So today when we start, I want to give you hint for one of the homework questions. One student asked me. Yeah. That's relatively hard, so I like to give you some hints for that one question. Yeah. Probably each class I can give you hints for 1 or 2. Yeah. I don't want to spend too much time, so today only one question. Question number 22. Yeah. Number 22. I gave that question in a exercise question set. Yeah. Yeah. So that's the question number 22. Yeah. So let me explain a little bit. So that's a relatively hard question. Yeah. So first, just remind you, so what's that question? Okay? Yeah. Homework number 1. Question number 22. Yeah. So what's that? Oh, sorry. Oh, covered? Oh, yeah. Not automatic. Yeah. Thank you. Remind me. Yeah. Yeah. Otherwise, yeah, good. Yeah. So first, let me describe the question quickly. Yeah. Given 267 element array, we need to use the minimum number of comparisons. Yeah. Find one element among the top 9. Minimum number of comparisons. That question, yeah, a little challenging, all right? Yeah. So here I like to point out the right direction of thinking. Yeah, Yeah. So one student asked me, yeah, sending me the thinking. I based on the, that student's message, also, my previous student feedback. Yeah. All right. So first, I try to point out a few common mistakes here. Yeah. The first, think about how many of you did in this way. Yeah. Top 9, right? Yeah. So one way did in this one. Yeah. Okay? Yeah. Find the minimum using n-1 comparison, right? Yeah. 266 comparisons. Okay? All right. But top 9, so then find, sorry, not the minimum, maximum. Because the largest, right? Yeah, maximum. Then find the second largest. Okay? Yeah. Because you can eliminate the largest. Then second largest, you use 265, and so on. Okay? Then the last one, find 9th largest. Okay? Yeah. So use what? 258. Okay? Comparisons. Yeah. If you do it this way, you can see it's not efficient. This way, not efficient. Don't do it this way, okay? Not efficient. Why? Yeah. What we need, we just need one element among top 9. Among, it could be anyone in top 9, one of the top 9 elements. That's what we need, okay? So what do we need? One of the top 9 elements. All right. Look at the first round. You already, after 266 comparison, you already get a top 1, right? Does top 1 belong to top 9? Does top 1 belong to top 9? Top 1 already belong to top 9. You already get a solution, right? Actually, you do more than necessary, right? Because top 1 is harder than top 9, right? Yes. So you overdo it. Top 9, you need this many comparison, 266. Or you already overdo it. That means you don't need this many comparison to get top 9. Yeah? Because if you use this many, you get top 1. That's harder than top 9, right? Yeah? What do we need? Just top 9. Okay? Yeah. Think about that logic. You overdo it. Okay? So, first, all these following 8 rounds, you can eliminate, okay? Yeah. Yeah. Even the first round, you already overdo it. Think about that. Overdo it, that means use more than necessary comparison. The answer should be smaller than this number. Okay? Yeah. Because we need less work. Less work, smaller number of comparison, less work to find the correct answer. Okay? Yeah. Think in this way. So that's one point. Okay? 1 point to the direction. Okay? Second point. Some students look at this 267. It's a relatively large number, right? Relatively large number. Because if you want to work on your scratch paper, how can you write this many elements on the paper? Okay? Too many. If you want to do experiments, too many elements. Yeah. So this situation is very common. Yeah. Sometimes I give you certain number of elements to work, but that number relatively large. Yeah. So here I give you one typical way to solve, to handle this situation. Yeah. All right. First, let's replace this concrete number by a general n number. How about that? Okay? Yeah. So we have n element array. Yeah. Because this concrete number is just a special case of n. Yeah. So we cover it. Okay? All right. Top 9, this number 9, we replace by k. Okay. So we find one among top k. How about that? General case, right? Yeah. General case. All right. Think about, if you can solve this general version, can you solve that concrete version easily? Right? Yeah. So here you can see the general version. Yeah. So we get it. But some of you may feel the general version is harder than that specific version, right? The concrete version. Yeah. Usually people feel, general version harder. Yeah. But when you have a general version, you have a little more room to manipulate. Yeah. What's the rule? You can try different n, different k, right? Can you change n to a smaller n, like 10, for example? N equals 10. How about that smaller number? You may feel better, right? Can you change k to another, like 2? Given 10 elements, how many comparisons you need to find top 2 among top 2, right? Yeah. In this way, you get a much easier question to work. How about that? Okay? Think about that. Yeah. The generic version, it looks harder, but you can try some simpler cases, right? Yeah. Simpler cases is easier, right? Yeah. Think about that. That's another thinking. Okay, another thinking. That's point 2. Okay, hint number 2. All right. Number 3. Number 3. Point. Yeah. You have the background, finding the minimum, right? Finding the minimum. Okay. All right. We're familiar with this solution, right? Finding the minimum. Finding the minimum the same as finding the maximum, right? Yeah. Essentially the same, okay? Yeah, so we can look at finding the maximum. Finding the maximum in n element array, how many comparisons do you need? N comparisons. N element array. How many comparisons you need? Minimum. Same as finding the minimum, right? How many? N minus 1. Okay? N minus 1. Yeah. N minus 1. Finding the maximum. Can you treat as top 1? Can you treat k equals 1? K equals 1. Top 1. Find the top 1, you need n minus 1 comparisons. Yeah. And the way to, how do you know you get top 1? Because you eliminate n minus 1 elements, right? Top 1, okay? All right. Now, when we look at the top k, among top k, how many elements do we need to eliminate if we want to get top k? How many elements sufficient to be eliminated if we want to get top k? Think in that way. Okay? Yeah. Because k equals 1, it's a special case. We just did before. Now you change that k, you can change to 2, 3, 4. You can change it to a different number. There, 9. How about that? Right? The same way of elimination. Top 1, top 2, the only difference is the number of elements to be eliminated are different, right? What's the difference between top 1 and the top 2? The number of elements to be eliminated are different. What's the difference between top 2 and the top 3? Okay? The number of elements to be eliminated are different. Then top 4, top 5. That number to be eliminated are different. At the end, top 9. These 3 points, 3 hints. Try to get the right track. How about that? Right track. After these 3 hints. Okay? Thinking. Yeah. So here, the goal, I designed this question. You need to practice thinking like this. Thinking, most important in problem solving. Logic thinking like this. Okay? Yeah. These 3 hints. Yeah. So when you go back, if you forget the details, you can watch the first few minutes. All right? Yeah. For this question. Yeah. Next time, if I see some other relatively hard, so I will give you more hints for other questions. Okay? Yeah. All right. Yeah. Now, string matching problem to solve it. Yeah. String matching problem this time. Yeah. Search keyword. Yeah. You can see, given a keyword, how to find the location of the given keyword in a given text, block of text, okay, article. Yeah. So you can look at different algorithms. Yeah, the fastest way to find it. Yeah. Here, when we start here, because the topic of this module, brute force, so we look at the brute force method. Yeah. All right. Problem number 5, string matching problem. Given a string of n characters, that's the text part, n. Okay. Total length, n. So it's an array, character array. Okay. A string of m characters, we call the pattern, the keyword. That one word, keyword. Shorter, much shorter. So m characters, we call the pattern. Yeah. So m should be less than or equal to n. Yeah. Then we want to solve how many comparisons we need to find a match. Or no match. Yeah. It's possible there is no match. Yeah. Still, it's a search result. No match is also a search result. Okay? If you find a match, you return the location of the keyword. Index. What's the location? Index of the first character in the keyword, in the pattern. That's the location of the pattern. Yeah. All right. Yeah. Find a substring of the text that matches the pattern. Substring. Okay. The problem. Yeah. All right. So then, let's apply the brute force. Everyone should be able to apply the brute force method. Yeah. Find its location. Yeah. All right. The index I of the leftmost character. That's the pattern location. Okay, our definition. Pattern location. First solution. Yeah. So there is an advanced solution in our textbook. Yeah. But here we do not talk about. That one is very difficult to understand. But in our textbook. Yeah. Very complicated. Yeah. All right. So here it's a straightforward thinking. Yeah. It's easy. This one is easy. Yeah. We need to have a mathematical representation of the question. Yeah. All right. All right. Because after we have the mathematical, then we can apply math tools. Yeah. If you do not have math representation, then it's hard to apply any available tool. Yeah. All right. Text, let us use an array, character array with indices 0, 1, last one, and -1 indices. Yeah. T, yeah. Text, yeah. T array, okay, character array. Pattern, P array, okay, yeah, with indices from 0, 1 through n-1. Yeah. Okay. 2 character arrays, yeah. 1 longer, 1 shorter. Yeah. Substring matching. Yeah. We want to look at the substrings in the given text in different locations and then do comparison with the pattern. Yeah. Brute force. Yeah. That's the brute force. All right. Requirement. How do you describe a matching state? When you get a match, there is a state. You need to describe it, the condition. How do you check you have a match? Okay, yeah. So here we need to describe it. So we find the location I. Yeah. Suppose at location I, we get a match. So what's the mathematical representation for that match at location I? Yeah. All right. So 1 to 1. Okay. Yeah. Ti equals P0. Yeah. Yeah. The first character at that substring, location I substring in the text, Ti equals the first character in the pattern, yeah, and so on. Yeah. Second in the text, same second one in the pattern, and so on. Okay. T plus J, the Jth character in that substring is the same as the J PJ. Okay, yeah. PJs. All right. Then the last one, yeah, I plus n-1. Yeah. So that's the description of a match. Okay, yeah, all right. Now, the strategy to do the comparison, yeah, to do this, character comparison. Here, in order to figure out the details, yeah, because we want to see how many substrings do we need to consider in the given text. For each substring, then we do comparison, describe it here. Okay. But we need to know how many total substrings we can consider. So here we take a simple strategy, guess and verify strategy. In order to figure out the details, we take the strategy. So what's that? So you will see it. All right. So let's do the thinking here. Can we exhaust all such m substrings? The length is m characters. So we call it m substrings. We want to exhaust all m substrings. So that's typically for a brute force. Brute force, we try to exhaust all the possible cases. If you can skip some of the cases, then it won't be brute force. Because when you can eliminate some of the cases, you need to apply special properties. Then, usually we do not treat as brute force. Okay? So here we do not apply any property, so we need to exhaust all the possible M streams. So the brute force way. Yeah. All right? Yeah. Every time extract an M substring from the text with consecutive characters. That's the way to extract M substring, one M substring. Compare it with the pattern for a possible match. Comparison, one-to-one comparison. Okay? Yeah. Question, how many such M substrings can you find in the given text with N characters? Can you make a guess? Yeah, look at the strategy, guess and verify. The first step, guess that number. Can you guess? Based on your intuition. Yeah. You have a text, the length of your text, N characters. Yeah. Now, from the beginning, you take the first M substring, then second, third, all the way to the end, right? You need to count how many such M substrings. Yeah. Here, if I draw a diagram, so this line, that's the whole text. You have N characters. Yeah. Then the first location of the M substring, then the last location, M substring, this one, M. Moving from first, each time you shift one character to the right? Only one character to the right to get the next substring, another substring, and so on. So you go through all the possible M substrings from beginning to end. How many M substrings can you find in the given text? That simple question. First, make a guess. Guess, not necessarily accurate, just close as possible. How many? Good. So you make a guess, M minus M plus 1. Any other guess? Different number guess? Any other different guess number? You want to try? You want to try? All of you feel this is a good one? Based on your intuition, okay? Guess completely based on your intuition. Make a guess. As close as possible. Then we will fix. If there is any problem, we will fix it later. Guess and verify. Any different number you like to guess? Do you understand why this plus 1? Why it's not M minus M? Plus 1 or not? Yeah. Because sometimes we're not quite sure, right, if we want to add that 1 or not. Yeah. Some students feel we need to add a 1. Some students feel, how about M minus M? Right? Yeah. So usually people make these two different guess numbers. Yeah. Now we need to fix it. Yeah. Because when you make a guess, usually it could be a rough guess, not very accurate. It's a rough guess, okay? Yeah. So our next step, verify to fix it. Because we need to check. We need to find a simple way to verify it. Here, yeah. We find a simple way to verify it. Yeah. All right. We want to consider a simple extremo case for the verification. Extremo case for the verification. So what's that? Yeah. A special case, because here we only require m less than equal to n. Okay? Yeah. How about the case m equal n? M equal n equals n, the same. It is extremo, but included. This case is included. When the text size and the pattern size are exactly the same, what's the answer? How many m substring? Exactly 1, right? Yeah. Now, m equals n, which one is correct? If you use the second formula, n minus n equals 0, that's not right, because it should be 1, right? So that tells you the first guess is correct. Because you try m the same, plus 1, you have 1, okay? Yeah, but we know there is 1, so simple, same. Yeah, so that's the point. Guess and verify. Okay, that's the point. Yeah. Later, we have a few other places, situations, we need to apply this simple strategy. Okay? Yeah. Yeah. Making guess, very important in problem solving. Yeah. You need to, many times we need to make guesses. Yeah. The closer, the better. Yeah. But not necessarily the same. So, because we can fix it later. Okay? We just want it very close to the destination. Yeah. We know there is a gap, but we can fix that small gap later. Yeah. So we don't worry. Yeah. But we need to make a good guess first. Okay. If you don't make a guess, you get stuck. Yeah. Because it's hard to make any move, right? Yeah. What's your next move? It's hard to make any move. Yeah. So you need to make guess sometimes. Yeah. All right. Yeah. So let's continue. Yeah. All right. Yeah. So here, not 0. So the answer is this is the answer. Okay. Yeah. Yeah. Because that one not right. Yeah. All right. Next, now, because we know the total number of M strands, we have that formula, okay? Yeah. Next, we want to fix the implementation detail. Yeah, because when we write the program, we need to use a for loop to go through all the M strings. For loop. When you use a for loop, you need to know where to start and where to stop, right? How many iterations do you need to do in your for loop? Yeah. At the beginning, your I equals 0. Yeah. So beginning, it's easy. Starting point, I equals 0. Yeah. But where is the end point? Yeah. You want to figure out what is the last iteration index number. For what index number, that's the last iteration. You should stop in your for loop. So we need to figure that number out. When you write the code, for loop implementation. Okay? All right. Yeah. So the last M substring is this one. Yeah. But the index T at this point, we need to figure out the question mark. So what's that subscript? Corresponding that subscript. How to calculate that subscript. Simple idea. Yeah. It's a simple problem, but we need to find some method to do it. Find some method to do it. Yeah, because here, look at our situation. Our M string moving, okay? Yeah. Moving M string from left to right, okay? Yeah, from left to right. Yeah. How do we keep track of the positions of M string? Yeah. So when you move some object, you need to keep track of the locations of the object. Okay? Yeah. So when the object reaches the end, then you can calculate its position, its location. Position, location, we use the subscript of the first character in the M substring for its position. Okay. Now we need to calculate that subscript number. Then in our for loop, we just put that number there. Okay? Yeah. How to do the calculation? Yeah. Here. Method. Yeah. All right. Remember in our first class, I introduced a concept called invariance concept. Still remember invariance concept. When we need to keep track of some certain information, we may need to discover some invariant property to help us keep track of our data. Okay? How to keep track of the data? Yeah. Invariant property can help us keep track of the data. Yeah. Here, when you move M substring from left to right, can you discover some quantity that never change? Certain numbers, certain quantity number never change when you move your M substring from left to right. Something never change. What's that? That's the invariant. That's what we mean invariant. Okay? Yeah. Can you see that? Some property never change when you move M substring. Yeah. How about the length of the substring? Is it a fixed number? It never changes, right? The length of the substring never changes, right? Never changes. All right. Or if we use another way, not necessarily exact length, the last subscript number minus the first subscript number, that difference never changes, right? That difference never changes, right? The difference between the last one and the first one, that difference never changes. Can we treat that difference as the invariance property here? That's the invariance property, okay? So we use that property to help us keep track of the locations of the M substrings. How about that? Okay? So here we have another chance to practice that invariance idea in problem solving, invariance. So we discover that difference. So invariant idea here. The difference of two end subscripts of each M substring. Difference. Okay? Now, the difference of two end subscripts of the first M substring, you know that difference, right? That difference is clear. Okay? What is the difference of the last M substring? We can calculate it. Okay? All right. So the first M minus 1 minus 0, that's just M minus 1, the difference of two end subscripts. Then the last M substring, unknown, we can use X for that unknown number. Okay? The last one, M minus 1. M minus 1 minus X, that difference should be the same as M minus 1, right? Yep. The difference never changes from beginning to end. Okay? So that invariance allows us to set up this equation. Then we solve for X. X equals N minus M. Okay? Then, when we write a for loop, this is the position of the last iteration. So I equals from 0 to this last number, right? Yeah. So that's the way you figure out the critical information. Yeah. Simple method. Yeah. So we practice. We use our invariance property, idea, to help us keep track of our data. Yeah? All right. So then, yeah, so the final last step, analysis. The best case efficiency, the first M substring happens to be the pattern. That's the best case. Yeah. You need to do M comparisons. Yeah? Because M character comparisons. Yeah. Yeah. That's best case. Worst case, you need to compare all the way until the last one. Yeah. So how many? Yeah. Each one M comparisons, but you have this many. Remember, in our previous slide, guess verify, we get this many substrings, M substrings. So multiplication, this many character comparisons. All right. Then the average case, can we add these two numbers divided by 2 for the average? Yeah. Here we can. Here, because it's a linear case. Okay? When you move substring, so along the line, so it's a linear function, right? Every time the incremental number is 1. Okay? Yeah? That's linear case. Even incremental, right? Yeah. Same every time, increment part the same. Yeah. Yeah. Then you can take an average like this. But if it's uneven, okay? If it's uneven, then it's dangerous to take. Because sometimes you take, yeah, so when you move for different cases, it could be a curve, all right? Yeah. If it's not a straight line, you cannot take difference. You cannot take, average like this. Yeah, because if it's a curve, sometimes higher, lower, uneven case. Uneven case, you should be very careful. Yeah. For example, later you will see for binary search, it's uneven case. Binary search, we do comparisons. Binary search for different key location in the array, when you do comparison, it's not even. Okay? Yeah, it's not even. So you cannot do it this way. Yeah. Yeah. So when you take average, you should be careful. Yeah. Is it a linear change case? The case among all different cases, the change along a straight line. Okay? If you draw a graph, it's a straight line. Then you can take, But if it's not a straight line, okay? Yeah, then you cannot take average like in this way. Okay? So be careful when you take average. Yeah. Think about it before you take the average. Yeah. All right. So that's the part D. Yeah. Yeah. Finish hint and part D. Yeah. So let's start our introduction to recursive algorithms. All right, yeah. Yeah, so Module 3, recursive algorithm. Yeah. So it's a basic, important topic. Yeah. Part A, introduction to recursive algorithms. 8.1, first view of recursive algorithms. Yeah. Yeah. Many of you should have some experience apply recursive algorithms. Yeah. But here we will learn, try to understand several aspects of this fundamental, important algorithms. All right. Recursive thinking first. First, we need to try to prepare ourselves, get used to the recursive thinking. Yeah. Because for ordinary people, in their natural thinking, they do not think recursively. Yeah. You have to get a training. In order to get used to recursive thinking, you have to go through some training stage. Yeah. Here, we do the training. Yeah. Why recursive thinking is important in problem solving? Yeah. Yeah. It's a very important problem solving technique or approach. Yeah. Yeah. We are used to straightforward, non-recursive thinking in problem solving. Yeah. So in general, people want to solve in a non-recursive way. Yeah. Only people get a good training, they can get used to the recursive thinking. Yeah. Yeah. All right. Some problems can be solved both non-recursively and recursively. Yeah. Yeah. So here we may like to compare these two different ways, advantages and disadvantages. Yeah. Yeah. Power of recursion. Yeah. Why people use recursive algorithm? The most important reason is this power of recursion. Very powerful. Okay? Yeah. So that's the biggest advantage of recursion due to its power. Yeah. So what do you mean the power? Powerful. Okay? Yeah. You can solve relatively hard questions in some relatively easy or compact way. Yeah. Short way, compact way. Yeah. Recursion, your code could be very short, but your solution actually, you can solve a relatively hard problem with relatively short code. Yeah. All right. Some relatively hard problems can only, parenthesis, be solved by recursion. Yeah. Because people argue any problems, if you can solve recursively, you can also solve non-recursively. Yeah. People argue that. Yeah. But it could be very hard. Yeah. Although you can argue, and some people try very hard to make it happen, but it could be very hard. Yeah. So we will see a simple example. Yeah. All right. Yeah. All right, so let's do comparison. Non-recursive way and a recursive way. Compare. Non-recursive way, usually we do iterative way. For loop, while loop, iterative way. Yeah. In that way, we avoid recursion. Okay? It's possible. Yeah. Another is the recursive way. We just call a function recursively. Yeah. An advantage for iterative way, usually it consumes less resource. That's the biggest advantage of iterative method, less resource. Yeah, but harder implementation, so that's the disadvantage part. Advantage is this less resource part. Yeah. Why less resource, I will explain. Yeah. And recursive, usually compared with iterative, we need to use more resource, but easier represent implementation. That's the advantage part. Yeah. Disadvantage, more resource, relatively more resource comparing with the iterative method. All right. Yeah. Here, let me explain why more resource. Okay. All right. You need to understand how recursion is implemented inside high-level programming language. Usually, high-level programming support recursion, right? Yeah. All modern programming language support recursion. Yeah. But they need to find a way to implement inside main memory. So we need to see that part. Yeah. All right. So here, let me explain the main idea in the recursion implementation inside the main memory. Okay. All right. Yeah. Here, let me draw a diagram. Yeah. Inside memory, when your recursive function get compiled and implemented and run inside the main memory, how does it work? Yeah. So compile, so convert it to machine language instructions. Yeah. All right. Then implementation needs to use a special data structure. The data structure is the stack. Yeah. So you learned the stack data structure, right? Yeah, before. Yeah. The stack has the property first in, last out, right? The stack, the main property, last in, first out. First in, last out, okay? So first, because you push into the stack, first in, that's last out. Okay, all right. So the first atom. Yeah. So for example, when you call a function recursively, yeah, suppose we have a function f. Yeah. When we call n, you calculate function value for n, it relies on the function value of fn minus 1. Then it relies on the function of previous one, n minus, and so on. So you can only find its value recursively. Okay? All right. So when you call f of n, yeah, because it's not available, then the implementation mechanism pushes this item into the stack. So at the bottom, f of n. Okay? Then, because it relies on f of n minus 1, then try to get f of n minus value, still not available, push it into the stack, f of n minus 1. And so on, okay? Not available, all right? All the way up. The last one, you need the value f of 1, but it is available, okay? Yeah, it's top of the stack, f of 1 available. Then you retrieve the value of f of 1, and you do the calculation, you can get f of 2. Yeah. F of 2 value available, you retrieve it, do the calculation f of 3. So that you can, finally, you do processing from the top, okay? Processing at the top. Then after that, you can retrieve that all the way down, okay? Yeah. One by one after another, then you get all the values in the stack calculated. Finally, you reach the bottom, you get f of n calculated. That's the typical recursion implementation. Okay? Yeah. it relies on a stack data structure to implement recursion. Okay? All right, not a problem. The resource used by a stack, because that data structure, you need to allocate the memory resource to the stack. And that stack could be deep, right? Yeah. That stack could be very deep. The deeper the stack, the more resource your recursive function consumes. Okay? So it needs a deep stack. It may need a deep stack. Yeah. But iterative implementation, you don't need a deep stack. Okay? Because every time you run a for loop, after you calculate it, then you can because the next iteration you can reuse the old memory storage locations, right? Because each iteration, the storage location temporary. Okay? You can recycle. All the temporary locations can be recycled. You don't need a deep stack. Okay? So the iterative interpretation, you need a much less memory resource. Yeah. So then you have a problem. Think about your memory size is fixed, right? Yeah. Your main memory size in your computer is fixed memory size. Think about if you work on a large problem, that means your stack could be very large, then your memory is not enough to hold that stack. What would happen? Because your main memory has a limit. But your computation requires a huge stack to store all the intermediate results of your recursive function values. What would happen? Well, stack overflow. So that's the stack overflow. That stack overflow, it's a runtime error. Runtime error. Then your program breaks. Your program, when it encounters stack overflow, it terminates. It breaks. Okay? That's the problem of recursive algorithms. Biggest problem of recursive algorithms. Think about how bad it is. Okay? Many times you like to avoid it. Many times you like to avoid that stack overflow problem. Okay? Try your best to avoid. But at the same time, you also want to enjoy the power of the recursion because it's so powerful. You can write just a few lines and solve a very difficult problem. That's the power of recursion. Okay? Yeah. Yeah. So that's our introduction, understanding of the recursion. Okay? Yeah. You need to know. Yeah. You want to get both sides, the power side, but same time avoid that stack overflow problem. Okay? Yeah. All right. All right. Let's move to next topic. We want to do the recursive thinking. We want to practice our recursive thinking. Yeah. Because we want the power. Okay? We don't want to throw away the whole recursive algorithm. So we still want its power. Let's do first a simple problem. Problem number 6. Calculate the factorial. It's easy. Yeah. We don't need a recursion here. Yeah, but here I just get you prepared in recursive thinking. Yeah. Given a non-negative integer n, we know the definition of the factorial, n factorial. Yeah. Yeah. It's a simple one. The first method, we can use iterative method, right? No recursion needed. Usually people don't apply recursion on factorial, right? Iterative. Yeah. Yeah. Just based on the definition of factorial, you can write a simple for loop to find its value. Yeah. All right. Yeah. But in this factorial definition, product of n consecutive integers, but we define 0 factorial equals 1. Can you understand this? Why people define 0 factorial equals 1, not 0? So 0 factorial equals 1. It's not 0. By your intuition, can you understand 0 factorial is actually 1, not 0? Yeah. How to understand that? Okay? Yeah? Yeah. 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 So we need to, yeah. Yeah. We will see it. There is a natural way to show it is 1. All right. Implementation for a for loop, it's trivial. Yeah. But method 2, now we want to practice our recursive thinking. Yeah. Although usually it's not necessary. Yeah. Here, we just want to do training on recursion. Yeah. Practice ourselves training on recursion. Okay? Idea. How to define a recursive function representing the factorial function. Factorial, it's a function. Factorial function. Okay? Yeah. All right. So here, we use some general problem-solving approach. Yeah. Divide and conquer. Yeah. Divide and conquer, another important topic. Yeah. That's our main topic in Module 4. Next module, we will study divide and conquer approach. Yeah. But here, we need to use that idea a little bit. Yeah. All right, divide and conquer. Yeah. All right. First, we use this principle. Remember, I mentioned this principle before. When the problem size becomes smaller, the difficulty of the problem usually is easier. Not 100%, but most of the time, it's easier when the problem size is smaller. Not 100% time, I use the prime factorization example to show. Sometimes smaller problem size could be harder. Yeah. But here, we use the general case. Yeah. The general case. Yeah. The problem size, when it's smaller, it's easier. Yeah. Here, for the factorial problem, when the size is smaller, it's easier to calculate the factorial, right? Yeah. That's true. That's true. Yeah. So we use that property. All right. Now, when you work on a problem of current size and factorial, that's the current size. Okay? All right. Assume that the problem of a smaller size has been solved. That's the recursion idea, recursion approach. When we work on n factorial, we assume a smaller factorial has already been solved. So we just use that result. Okay? Yeah. That's the typical thinking approach. Yeah. All right. But there is a gap between those two sizes. Current size, previous problem size, two sizes, there is a gap. Yeah. So we need to fix that gap through a recurrence relation. Yeah. So let's apply this method here. Okay, yeah. All right. Analysis. Yeah. So this factorial definition, we define f function, f of n, representing this factorial function. All right. After this function defined, then we apply divide and conquer. We cut our data into two parts, smaller, divide somewhere. Okay? Where to cut? We only chop off the last operand, n. The last operand, we chop it off. Okay? So divide, then conquer. Yeah. Divide, so our data, two parts of the data. The first part, we can use factorial function f of n minus 1 to represent it. Recursion, previous one, recursion. Yeah. Then the single piece one, and one, just one operand. So now our formula, our recurrence relation becomes f of n equals f of n minus 1 times n. This simple recursive relation. Recursive relation, so simple, yeah. But it's recursive. Okay, yeah. Recursive. Yeah. All right. Yeah. So we can implement it in this recursive function call. Okay. Although, yeah, if you're doing this way, it would be worse than the iterative version because the stack, much larger. You use much more memory resource. Okay, it would be slower than the for loop way. Okay, yeah. But here we just practice our thinking. Okay, we won't really use this way to write our code. Okay, yeah, it's a better one. Yeah, all right. But we can use this formula to help us understand why 0 factorial equals 1. Okay, makes sense. Yeah. Otherwise, by our intuition, it's hard to see why 0 factorial equals 1, right? Yeah. Yeah. To understand that, let's look at this formula another time. This time we write f of n equals f of n minus 1, left-hand side, equals f of n over n. Yeah. So from this recurrence relation, you can see that easily. Okay, both sides we divided by n. Yeah, so we get that. Now, let's plug in n equals 1. It's legal, right? Yeah. We plug in n equals 1. It's legal, both sides. Left-hand side, f, when n equals 1, it's f of 0, right? Right-hand side, f of 1 over 1. F of 1 factorial is 1, right? 1 factorial. Over 1 over 1 is 1. But left-hand side, f of 0, that's 0 factorial. That's 0 factorial. Okay? 0 factorial equals 1. Okay? You can see? Yeah. This tells us, if we assume, because 0 factorial is 0, this is our assumption. Because we assume that's our assumption. If we make this assumption, then it's compatible with our factorial formula, right? Compatible. The formula compatible. If you make a bad assumption, then your formula, your result won't be compatible with the original formula. Okay. Here, this assumption is compatible with the original formula. That's a good assumption. Yeah. Otherwise, you get contradiction. Okay? Yeah. You cannot make any contradiction. Okay? Yeah. Yeah. So that's the reason we make this assumption. All right, so let me finish this one. The next topic, I will show you the power of recursion. Power of recursion. This one just practice simple recursion thinking, recursive thinking. Next one, we will solve another puzzle problem using recursion. You can appreciate the power of recursion. All right, that's it.